Okay, I'm now going to actually seriously get into the WebAssembly stuff. But first, uh, I've got a couple of minor changes that I've made that I'll just quickly go over to basically make it a little bit easier to see how you would load this. So I've moved out the loader. This doesn't really do a whole lot. It just maps the existing symbols to the uh, the endpoints that are going to be using them. So here we've got next steps, which is a symbol that is a function, um, and I've just got this nice little wrapper which wraps around it because it will take integers as input and integers as output. And that's really all there is to that. We've got this separate thing here, which is a memory buffer, as it states. This is essentially shared memory as far as this is concerned. So it's a place where the WebAssembly can put stuff and where it can be extracted, like in this location here. So this is actually just this function here is doing a reasonable amount of work, and it therefore produces 8 different values, and those 8 different values are actually stored in the shared memory, and we just use the information that it returns, which is just an offset, to work out where in the shared memory to look for the actual results. So scrolling back down here so that you can see I've also split out the import. So what this is actually doing, this is providing symbols which will go into the WebAssembly for the WebAssembly's use. So this means that this is actually exposing a symbol called log. I'm not sure if it's console.log. I will have to check, but I'll get back to that one. But yeah, that's how you expose the JavaScript context to the WebAssembly stuff. So this is originally what I had here, and this is I'll show you this one. Yeah, so this is the page that I use locally. So when you're running it locally, you don't have permission to implicitly load a WebAssembly file. So what you actually have to do instead is make the user choose it. So it's this thing, this WASM file. And having done that, I've got everything set up so that when the file is selected, it's loaded. So that's it done now. But I'll actually show the behavior so that you can actually see that there is a difference. So if I dial this up a bit, so normally I go for like 200. Just do a random test. There you go. So it takes like a couple of seconds there. If I turn display updates off, so this will be quicker. That's because the way that it handles, the way that I've written the display updates thing is that it yields back to the browser at a regular basis, and that means that it'll take a certain amount of time to re-render everything. So if I just do, you can see the runtime on the right. If I just do a random test again, this will be quicker. Okay, so sometimes it can't find a route. And yeah, when it can't find a route, that normally happens pretty quick. So I'm just going to run it again, and I'm going to run it again. And okay, there we go. Right, got there in the end. Right, so it takes 100 milliseconds. That's a fairly typical amount of time, just running from the JavaScript. Yeah, there you go. So there's 95 milliseconds. So if I've loaded the WASM file and then run it again, yeah, so you can see 46 milliseconds. So it takes about half the time. It's not an enormous difference, but what I wanted here was to really get the runtime reduced to see how low I could take it. So that's how the this loader is working. So this actually uses an HTML input element, and yeah, you can understand this if you're familiar with how file reader works. But essentially, all that it does is it takes the data and then it shoves it into WebAssembly, and WebAssembly nicely will convert it for you, and then you just do the linkage. So if you are on an actual host, you don't have to do that. I mean, you can see, in fact, that this is slightly longer, but this will involve no user input. So here you can see this just uses fetch. The fetch API, you might think of it as $.ajax if you're used to jQuery instead, but it does the same thing. It just asynchronously fetches a thing, unless you ask it to not be asynchronous. And ideally, you end up in this branch here, this instantiate streaming, which is a nice little wrapper around doing all the rest of the stuff. As it happens, Safari does not have that, so I'm stuck in this little section where I have to actually get the response, turn it into an array buffer, and then run it into WebAssembly.instantiate. So basically one further step. And I can show you that because I do have something running on localhost. So I'll just reload this. Right, and I can show you, now that I've established how long it takes to do the 200 corner to corner, I can show you that this has actually loaded the WebAssembly. As soon as I get something that's not a miss, and as soon as I remember not to have display updates on. There you go, 41. So you can see it's about half the time of the JavaScript time. So this has loaded. I've actually got it emitting a message into the console so that I can check that specifically, but for this purpose, I've already checked it. I already know how this works, so I'm not concerned. So I'm actually going to commit these changes now. So this will make my life slightly easier in future. You might notice that there are some syntax errors here. So this was previously m.exports. It was the version which I had not specified, and therefore I hadn't seen that content at had not been given a specification. So I will come back and deal with that. This one is, strictly speaking, a quirk of how Visual Studio Code works. It doesn't assume that you have an HTML document as your document, and therefore document.querySelector, as far as it's concerned, might be returning any kind of a generic element. So I need to tell it that it's an element of a particular. Well, I need to tell it that it's an HTML input element, but also specifically I need to tell it that it's an HTML input element. In other situations, if I were writing this as generic library code, I would probably stick a guard case in here. You have seen those before, so that's the if e instance of HTML input element, blah blah blah. At the moment, I'm not going to deal with that, but I will come back to it and deal with it eventually. So now I'm just going to add a quick commit for this. Split the loader so that it can work online. There you go. Right, I'm going to get straight into the WebAssembly, but the second I do that, everything's going to instantly become more complicated. So if you're looking at this from a JavaScript perspective, you will think, well, you probably will like the syntax highlighting, because why not? It's lovely syntax highlighting. But you'll notice that it's nothing like JavaScript. It has nothing in common there. So I need to take a little bit of time to explain what on earth is going on here. So to start with, so WebAssembly isn't actually an assembly language in the sense that you might look at i386 code. It is assembled, of course, and it does have similar low-level operations, but there is a key difference here, which is that WebAssembly is actually stack-based. So you can see where all of these brackets are. So we've got various terms which are in brackets after the thing. What that actually does is that puts the relevant output, well, it puts the relevant value before the statements which precede it, which sounds a bit crazy, but so basically to show you, and I don't guarantee that this is correct, but I believe this is the right way around. It would actually be like that, and you can see that that doesn't like it at all. So I probably have got something wrong there, but yeah, in essence, that's the idea. It's working this is telling it that it needs to work in the opposite way around. So I'm going to quickly go over how stacks work in terms of functionally doing stuff on the stack, and I'm going to do that in probably the cheatiest way possible by doing it with numbers, not with actual commands, although mostly doing it with numbers. So if you're familiar with Linux, you probably know that there is a function called BC. Of course, not just Linux. Here I am on the Mac, so it also exists on most Unices. And this is just a calculator program, so you can just do, you can 1 plus 2. You can do log. I guess that's let's do log 3. Yeah, there you go. And that must therefore be a power 2 log, not a e log. Actually, no, maybe that is an e log. I mean, I might be completely wrong on that, but whatever. It doesn't really matter. It's a log function. So I'm going to give an example of a simple percentage increase calculation. So that might be 999 multiplied by 100 plus 20 over 100. So that's adding 20% to it. You can see it's 1199. We got the floating point problem here, where it's not quite expressed in the way that you would want it to be, but it's so 1199 is the amount that we would be expecting to get out of this. So when you put this into BC, in fact, BC doesn't do that work. It laughs at you. It actually has a backend called DC, which runs that runs as a stack-based operation. So where we had all of the brackets here, DC does not care about that stuff, or rather, it does not use that stuff. It says, no, you will present things to me in an order I like, and then I will deal with it. And I can show you. I can show you how that works quite at a simple level. So if you have the first calculation we've done there, 1 plus 2, that would actually be written as 1, 2, plus. And I have to do p at the end to tell it to emit the number. So here we have the number 3. And what it's done is it's essentially, you can think of it as working backwards, and that might be easier for you if you think of everything as bracketed before it. But in practice, what it actually does is work forward. So it sees a symbol that's a number, that's an immediate value. It shoves that onto the stack, and then it consumes the next thing. That's another immediate value, so it just shoves it onto the stack. So the stack now has 2 at the top and 1 just behind it. And then it sees the plus operator, which says, fetch the top 2 things from the stack, that's 1 and 2, add them together, push the result back on the stack, which is the number 3. So the stack now just contains the number 3. And then P will consume one element of the stack and print it. So for this more complicated one, I'm gonna write that out in full in a minute. But the thing to keep in mind is that the exact order that you do things in can avoid the need to actually have bracketing, to have special processing. So in the same way that a human would deal with this, a human would look at this number and would say, well, that's 120, okay, I'm immediately resolving that. I'm going to write 120. And then probably a human would say, well, I can recognize that 120 over 100 is 6 over 5. So that's the actual number I'm going to deal with. And then you would say 999 multiplied by 6, which you can work out. It's not that difficult. And then you would divide it by 5, which perhaps you might have a little bit more trouble with. So having done all of that, you as a human being didn't use brackets at all. You didn't have a special place to store all of this stuff. You were always operating on recently used values. You always knew where you were. And although that doesn't work very well for very complicated situations, it does work well. It does work well for small ones, and there is a solution for more complicated ones. So here, what we would actually do, first I actually need to set the precision, and 2k is how you do it, so 2 decimal places, please. So you can still put 999 where it is. Obviously, you can't put the multiply symbol next. And actually, what you will want to do is just immediately get straight into the brackets. And of course, you can't do the plus symbol there either. You have to put the next value, then you put the plus. So at this point, I'll have 999 and 120 on the stack, and then star, which will give me my 999 multiplied by 120 value, and then I can add 100 and a slash. So it will operate in the order that you expect in this case. So the value that is further left on the stack is the one that's divided by the value that's further right on the stack. Although this is a point of confusion with a lot of stack-based languages, particularly if you have the opportunity to move stuff around. And of course, P at the end to print it. So here we have 1198, which is, yes, it's technically incorrect because it's not rounded, but yes, here it's obviously truncating the value because it hates me. But that's basically how the stack-based operations work. So it's not overwhelmingly difficult to deal with, but it is a very different way of doing things. And that's why we have all of these brackets all over the place. That's so that you don't need to deal with stacks as much as you otherwise would need to. So here at the top, I'll look at that. I've answered my earlier question about whether console and log are actually separate symbols. Yes, so technically they are separate symbols here. So this obviously accepts two values and then maps it to a function which takes a single argument, which for this purpose is just a number. So this is a somewhat interesting case because here I'm literally just logging numbers. If I go back to console.log, yeah, here it is. This is just taking a number. That's all it's doing. So this only allows me to dump out numbers. But if I were inclined to dump out strings, what I could do is have a function which will still take a number, but that number is an offset into the memory, and I can stick a string in that memory before I do anything. So this one doesn't have a defined return. If I recall correctly, you would have to have a defined return if you are returning something. It's a slightly different situation. So here, here I'm declaring a symbol that will be called mem. Nice and simple. And actually, is this symbol the same one that same number that I'm using? No, it's not. So buffer is the one that I'm using somewhere else. So this symbol is called mem. So in other places where I refer to mem, it will be this chunk of memory. And in this case, it's asking for 10 pages because for some reason, pages were the desired memory size for this. So as you can see, I've nicely commented this is 640 kilobytes with a nice little winky face. Um, just to remind myself, mostly. You might notice that double semicolons are how you do the comments in here. I don't think there's actually any restriction on using forward slashes, but perhaps that's just more consistent with assembly. I honestly don't remember what real assembly looks like. So after the memory, we've got this thing, and I'm just going to call it a thing at the moment. But you can see that it's the function. So I've declared that this symbol is global, and therefore it is available to everything that's inside this module. And actually, technically, I think also available to things that are outside this module, which is useful for exporting. No, it's not. No, look at that. I've immediately contradicted myself, but I'll get down to that. So here I've defined a symbol, and apparently that means it's a function. I'm not going to look it up. I've wrote this before. I don't need to look it up. So this is saying it returns a mutable value, I believe, which I think is primarily just a hint to copy it on the way out rather than retain it. And it indicates that it takes an argument, which is defaults to 0. I guess I'll find out in a minute, because I have... Oh, no, you know what? I have confused myself completely. These are not functions. These are values. Which, I mean, this is the experience of writing in a language you don't write in very often. You don't necessarily know what's going on there. So yes, okay, these are actually just values. So this is mutable. It is a mutable i32 value, which is to say it's a 32-bit integer, which I believe is unsigned, and it has a default value of 0. That makes much more sense. So here you go. Node width equals 0, basically, is this value. So these ones, pos offset, store offset, and empty node. So I believe because they don't have the mut in front of them, they are not actually changed. They are not actually values that can be changed. So they have that initial value and then never afterwards, and it would ultimately be a compile failure if any of those things were to receive an assignment. After that, you can see my exports. So these are very straightforward in terms of if you're looking at it, you can see very easily what's going on here. This is exporting the function called $addNode, and it's exporting it with the name addNode. It's very simple. So these take an argument which is a symbol definition, I believe, which is why most of these have func in front of them, and this one has memory in front of it. I would absolutely blame myself for this. I don't think I should have used a different name externally to the one I used internally. I think that was a little bit stupid, because it will just confuse me, and indeed it has confused me already. But also in general, it's a bad idea to use a name which is also a keyword and which is also a generic concept. So I've kind of made a big mistake here, but at the same time, I know that this module, in terms of how it communicates with the rest of the system, is not really going to be able to say, here's some specific memory, particularly because the limited size I'm giving it is going to make it very difficult to have special purpose memory. Okay, so here we've got an actual function, addNode. You might notice I have put them in alphabetical order. I've kept myself fairly strict with that. Oh, look at that red. There's some red there. I don't like that. So perhaps that doesn't work. Although, I mean, it did work before. It's compiled before. But it's possible that it doesn't work now. I'm actually going to just have a quick look, because I left myself a README, which Just waffles about a lot of stuff. But surely this README tells me how to actually do it, how to compile it. Do you tell me how to compile it? Apparently not. Okay, well, I'm not going to be doing that this time then. So I'm suspicious of this. I'm suspicious that I'm seeing some red here. Hopefully it's not a real problem, but I will see at some later point. If I look further down, I do have some shorter ones, yeah. So here's a much better example. So this is a function called $byteat, and it's immediately followed by the arguments it takes. So these are declared as local values. So there will be a local value called $x, which has type i32. They will actually pop values off the stack, but that will only work if the stack size is actually that size. This is actually one of the complexities that's involved here that I have run up against, and that's one of the stronger reasons to use the brackets, because the brackets define exactly what the stack is, whereas just using the stack as it currently is can cause a problem if the stack is a little bit deeper than you're expecting it to be, and obviously can cause a problem if it's shallower. So if we see where a value is where a function is actually called, which probably is present above somewhere. Yeah, here you go, call set byteat. So this is done with a bunch of brackets following it, and therefore it knows exactly what the stack is. So this is called with a stack of exactly 3 items. You can never get it wrong. It's very straightforward. Unfortunately, you don't get any kind of syntax checking for this. I mean, there will be systems which could, but for this particular program, Visual Studio Code, it doesn't understand that. It knows that how the syntax is structured. It doesn't know that I've made a mistake if I delete one of the arguments. So, following the params, as you can see, it declares what the result is. Technically, that does also allocate storage, I think, but it doesn't really make any difference as far as this is concerned, in terms of the fact that it could allocate storage at the end. This is just saying that there will be a value which is of this particular type. So at the end of the call, there must be one item in the stack, and that must be the type of it. So after that, we've actually done with the function prototype, as you might think of it, and we're into the actual way that the function works. You might notice I've put a comment saying making a statement that's completely contradicted by the actual type that's involved here. The reason for doing that is because in general it's easier to pass around the same types all the time. If you have a lot of different size types, it can be harder to tell where exactly the limits are of a value that you're dealing with. But also, some of these, and I think probably not byteat, no, not byteat, but some of these do return values, and where a value is returned, it may also be a little bit complicated returning a value which is less than 32 bits, although I don't particularly recall. This is a file that I've had for a while, obviously for more than 6 months, so I don't have specific memories of why exactly I wrote that. Okay, so I've now chatted for about half an hour, so I'm going to put an end to this now, and next time I will come back and hopefully finish talking about this.